NVIDIA Graphics DevTools to make high-performance ray tracing applications. My name is Aurelia Reese, and I'm the Director of Graphics Developer Tools at NVIDIA, where my role is to ensure that developers have the best experience developing their graphics applications as possible. Today, we're going to look at how you can leverage NVIDIA Developer Tools to help you create amazing 3D graphics applications that take advantage of ray tracing to create stunning visuals. We've got a lot to cover, so let's dive right in. First, I'll give you an introduction to the NVIDIA Developer Tools team and what our mission is. I'll then walk you through the anatomy of a ray tracing application and how you can use Nsight Graphics to debug some common problems. After that, we'll look at a specific profiling feature called GPU trace and how you can use the generated traces to analyze performance limiters. We'll then have a look at how NVIDIA GPU schedules shaders and how the shader profiler can provide in-depth information on how to improve shader performance. I'll fill you in on how the Nsight Perf SDK can be used in a real-world application to gather offline metrics. Finally, I'll show you how Nsight Aftermath can be a valuable tool to identify and resolve GPU crashes. And we'll end with some conclusions. It's worth mentioning that I'll be available to chat during the session, so if you have any specific questions about topics I'm discussing, feel free to click the Ask the Presenter button and submit your questions. Let me start by telling you about a world-class organization.
NVIDIA is world-renowned as a leader in computer graphics, AI, and data center solutions, and a large reason for that is due in part to the powerful ecosystem that we have created for developers. We have enabled cutting-edge 3D graphics thanks to the GeForce RTX line of GPUs that provide powerful computing ability and cutting-edge features like ray tracing. NVIDIA Developer Tools is an organization that spans multiple areas including compute, system software, and graphics. Our mission is to help developers to be as productive as possible by creating useful tools for gaming, workstation, automotive, and embedded systems. These tools are meant to help developers squeeze the most performance and graphical fidelity from NVIDIA GPUs. Ray tracing is a great example of a technology that few thought would achieve mass industry adoption, but is now available on most major gaming consoles and from every GPU hardware vendor. Of course, that wasn't always the case. Over 40 years ago, a single frame could take up to 40 minutes to render. At the time, Turner Whitted jokingly proposed that a fleet of room-sized Cray supercomputers, each rendering a single pixel, could achieve real-time performance. Today, this is possible on a single NVIDIA GPU. DXR was the industry's first accepted API for real-time ray tracing. Introduced running on a DGX2 workstation at GDC 2018, real-time ray tracing became available on a PC GPU through Turing architecture GPUs. Today, you can get real-time ray tracing on the Ampere architecture-based RTX 3060 Ti at a very affordable price point. In 2020, the Kronos Group officially ratified and launched the Vulkan ray tracing extensions, providing real-time ray tracing to even more platforms and potential users. Today, games such as Doom Eternal take advantage of ray tracing to increase realism and immersion, and because of this, it's important that every developer become familiar with ray tracing to some extent. NVIDIA was involved in the development of both APIs, and their design is heavily inspired by the NVIDIA Optics ray tracing API for CUDA. Be sure to read the 2009 white paper to understand the problems it was attempting to solve. I'm not going to cover advanced ray tracing concepts like secondary bounces or algorithms like path tracing, but I recommend reading the free Ray Tracing Gems 2 for a great explanation. All of our tools work with the groundbreaking NVIDIA Ampere architecture, which includes the RTX 30 series GPUs. We've even enhanced a few features to work even better with Ampere, like GPU Trace, which now shows you more metrics that provide additional visibility as to what is happening on the GPU. There are 4 primary tools that we provide to developers that are creating graphics-intensive applications. Nsight Systems, which helps debug and profile system-wide CPU and GPU interactions. Nsight Graphics, which helps to debug and profile graphics APIs like Vulkan and Direct3D. Nsight Aftermath, which helps you identify the reason for a GPU crash. And the Nsight Perf SDK, which allows you to integrate metrics collection directly into your graphics application. Let's have a look at how Nsight Systems can ensure that your CPU and GPU are working together most effectively. Development tools are meant to save you time and frustration, and one of the best ways to do that is to ensure that you have an efficient and effective workflow. What we recommend is to start by defining the problem. Is it a performance issue or something wrong with rendering? If the issue is rendering related, Nsight Graphics is the best tool for the job. We have many features to help resolve these kinds of issues, and we'll get into that in a bit. If it's performance, first identify if the problem is GPU or CPU related. This is a place where Nsight Systems shines. If it turns out that the issue is GPU related, you can easily switch over to Nsight Graphics and start doing your analysis there. After a few optimizations, you might move the needle in the opposite direction, and it's easy to go back to the other tool to solve new issues that might emerge. This analysis takes time and careful consideration to balance workloads between CPU and GPU. Let's look at how that looks at first glance with Nsight Systems. Nsight Systems is a system-wide performance analysis tool designed to help developers tune and scale software across CPUs and potentially multiple GPUs. It offers wide-ranging support across a multitude of operating systems and graphics APIs, including Vulkan and Direct3D. With it, you can see graphics queues, threads, and call stacks, as well as CPU work duration for functions and user-placed events using PIX and NVTX markers. Nsight Systems also works for ray tracing applications and has some truly powerful features to help identify and resolve performance issues. On Quake 2 RTX, for instance, you can see how well the renderer is utilizing multiple GPUs to achieve full path tracing with a fluid frame rate. You can view the WDDM queue to ensure that work is being efficiently submitted to the GPU. There's also the ability to do stutter analysis, allowing you to visually identify the root cause of a stutter so that you can ensure that the frame rate remains consistent. A great place to start when first getting to learn Nsight Systems is by looking at a timeline of the application's execution. This view consists of several rows that visually represent how the application is interacting with various system resources over the course of the application's lifetime. You can see the markers that were placed for a graphics API, as well as durations for API events. The event table provides even more detailed information that can be expanded in the event description. This lets you get a breakdown of the constituent parts of your scene and determine where the trouble spots that you should focus on are. Nsight Systems supports sampling thread call stacks and showing a statistical breakdown. This is especially useful if you want to see where most of the execution time is going in your frame. Thread activity is an incredibly important indicator that provides a quick overview of where your algorithms are spending the most time. Command creation and synchronization can create a lot of bubbles in your frame time, and this view lets you see exactly when GPU work actually begins. Seeing lots of gaps between the events in the graphics queue and actual GPU execution is a great way to see if you are properly feeding the GPU. What I mean by that is that you always want to be providing your GPUs enough data to stay busy while you're doing other things on the CPU. This workload parallelism is what lets you fully leverage system resources. It's incredibly important for modern applications to reduce mid-frame calculations that result in frame rate stutters. While poor frame rates are unpleasant to deal with, stutters are a big enough distraction that it ruins immersion in the game world. To help with this, there is a dedicated frame health row that allows you to see when an API command is taking too long to execute and thus resulting in the GPU not being able to process new commands fast enough. In this example, the application is compiling a shader in the middle of rendering the scene. The programmer can now easily see this and move that shader compilation to a better spot, such as at scene creation or as an offline process. Another thing that is incredibly important for good performance is reducing the amount of memory paged to the GPU. You can visualize all available and use memory for one or multiple GPUs. With this data, you can make sure that you are not oversubscribing resources. In addition, you can see how efficient PCIe memory transfers are, especially when utilizing the new resizable bar support that is now available on NVIDIA Ampere GPUs. Now that we've had a look at how Nsight Systems can help you to optimize your CPU and GPU interactions, let's look at the case where there are graphics rendering issues on the GPU. As our handy diagram showed, we'll use Nsight Graphics for this. It supports operating systems like Windows and Linux, x64 processors, and soon, ARM processors as well. Modern graphics APIs like Vulkan and Direct3D are supported, as is OpenGL. We support many features going back to the Pascal graphics architecture, but Nsight Graphics especially shines with modern RTX GPUs that utilize the Turing architecture or the Ampere architecture. 3D graphics APIs provide the mechanisms for you to load objects into GPU memory and then to specify when you want to draw them. We call these API events, and every 3D graphics scene is composed of many of these events. These events are straightforward to browse, and in addition, we give you a detailed view of what parameters were used for that event. For example, in Vulkan, to start ray tracing, you call the VK command trace raise KHR event. In order for this event to work properly, you need to define storage buffers, acceleration structures, shaders, images, and samplers that describe the 3D world. The API inspector allows you to see exactly what parameters were specified by the programmer. This is incredibly useful since missing even a few parameters here might result in incorrect rendering or no rendering at all. Graphics applications utilize resources like textures, render targets, shaders, and buffers to generate the scene. When a rendering artifact or bug appears, it's likely due to some misconfiguration of these resources. With Nsight Graphics, you can visualize all of these resources using a built-in browser. You can sort by properties like resource size or format and see how many modifications occurred for that resource over the course of the frame. For example, let's say there was an object in your scene that was drawing without the correct texture. You can inspect the draw call, look at the associated resources, and determine if the reason is related to the geometry, the textures, or the shader that applies material properties. Perhaps there were vertex attributes that were incorrectly loaded from the geometry file. The resource browser allows you to specify a memory structure definition to allow you to more easily inspect values. For instance, if you specified the vertices and normals correctly, but the texture coordinates were loaded incorrectly, you'd be able to clearly see that. Acceleration structures are especially important for ray tracing and deserve special attention to ensure that they are set up properly. To help with this, we provide a dedicated acceleration structure viewer that gives you a plethora of information. Let's take a few moments to learn more about how ray tracing works so that you can better understand how Nsight Graphics can help. Ray tracing involves shooting rays from every pixel on your screen and determining what they intersect with in your virtual world. In order to do this quickly, the world is subdivided into a top-level and bottom-level acceleration structure, also called a TLAS and BLAS. The TLAS contains instances and transforms for the BLAS that it points to. The BLAS maintains an axis-aligned bounding box, or AABB, along with the geometry to render. Acceleration structures help to speed up ray traversal across the world, since doing a coarse test on a simpler shape, in this case the AABB, is much faster than testing for a triangle intersection directly. NVIDIA Turing and Ampere architecture GPUs have specialized hardware to do this efficiently, but even so, it's very important that these structures are properly fitted to geometry in order to ensure as few AABBs are tested as possible. It's your responsibility to supply top and bottom level acceleration structures and to efficiently update them for dynamic objects. There are a few new shader types you should be familiar with. Ray generation shaders are where your rays are spawned. This is effectively the entry point for the trace rays or dispatch rays API call. Closest hit shaders are run when a ray intersects with scene geometry. Miss shaders execute when a ray does not intersect with anything in your scene. You might put your skybox code here as an example. Intersection shaders allow you to provide your own primitive intersection, for instance spheres instead of AABBs. Any hit shaders run when there is a non-opaque intersection and you would like to modify the intersection result. This is useful to implement alpha testing since you can permit rays to keep going. There's also a new shader type known as callable shaders that acts like a subroutine, allowing you to dynamically execute a shader from within another shader. This helps to cut down on the number of shader permutations needed and reduces the need for uber shaders and excessive conditional branching. Since acceleration structures are so integral to ray tracing performance, it's important to keep in mind these key areas to ensure that your scene is set up for peak performance. Number 1, optimize your acceleration structure build update using pruning and selective updates. Number 2, use asynchronous compute queues to overlap build or update with other work regimes. For example, you can calculate physics on one queue while updating or denoising on another. 3, keep low the number of barriers used in order to avoid serializing TLAS and BLAS building. 4, batch or merge your build update calls. 5, mark geometry opaque as much as possible. 6, reduce the number of instances that overlap to improve ray traversal performance. And 7, ensure that large instances do not include too much empty space. Consider breaking these down to reduce the area of the instance AABB. Nsight Graphics now includes 2 new performance analysis features in the acceleration structure viewer to help with overlap and sparsity considerations. The acceleration structure viewer allows you to zoom directly to any top or bottom level acceleration structures instance by double-clicking on the list to the left. In order to determine how many instances are overlapping, you just click the Instance Overlaps button, which brings up the analysis dialog. The view also changes to colorize the excessively overlapping instances, allowing you to quickly hone in on the most important instances to improve. The same applies for instance sparsity, which might result in traversal that never actually intersects with geometry due to empty space. This is incredibly inefficient, and the analysis dialog allows you to zoom in onto the AABBs that should be modified to reduce their sparseness. Now let's look at profiling with GPU trace. When you need to improve your GPU performance, timing information is nice to have as it provides a picture of where you are over budget, but it doesn't necessarily tell you how to improve performance of a given work regime. With GPU trace, you are able to see low-level metrics that map directly to GPU hardware. It's an activity within Nsight Graphics and can be launched much the same as a standard frame debugging or profiling session. Unlike C++ captures, traces can be saved out and referenced later without requiring the original system configuration or replay. You can even open a Windows trace on a Linux machine, and vice versa. GPU trace works around the concept of performance metrics that are laid out in tables or on a graph. These metrics provide you with the state of the different hardware units, which allows you to determine how to better utilize available resources and reduce dependencies. You can correlate frame performance using user-defined perf markers as well as API events like trace rays. With this tremendous amount of data on the GPU state, you can pinpoint exactly where your performance issues are coming from. As an example, I had mentioned that you should take advantage of asynchronous compute queues for building your acceleration structure and other regimes simultaneously. With GPU trace, you can visualize this to ensure that your code is functioning as expected. Metrics, which are also referred to as performance counters, are measurements taken for different parts of the GPU. These measurements help paint a picture of how well the GPU is performing. Similar to the gauges in a conventional car, these metrics help you determine if your engine, so to speak, is working at peak efficiency. There are hundreds of different metrics you can use to do this, so we try to curate a smaller list that encompasses the most significant causes of performance degradation. For example, the GPU has a number of hardware units that work at the lowest level to execute shader instructions efficiently. These might include the text unit, primitive engine, L1 cache, RT core, front end, as well as color ROP and ZROP. For a deeper understanding of the NVIDIA architecture and hardware units, check out the NVIDIA Ampere architecture white paper on the NVIDIA website. Metric values are different depending on what is being measured. In the same way that the engine vacuum gauge is not measuring the same thing as the RPM gauge, GPU performance metrics have different measurements. I won't cover all of them here, but keep in mind that some of these values you want to be low and some you want to be high. When considering percentage values like throughputs, 100% is not usually desired as that implies that you are saturating that part of the graphics pipeline. Being too low means that you're not utilizing it effectively. We recognize that becoming a GPU expert that understands every performance metric requires a tremendous amount of time and training. We thought about how we could make this information more accessible and easier to interpret. That's when we came up with trace analysis. Trace analysis is a rule-based system that looks at the metrics saved in the GPU trace report and categorizes the work regimes associated with those metrics based on the likelihood of improving performance if those work regimes were optimized. In addition to providing the potential gain, we provide a description of the rule and recommendations on the steps you can take in your code to realize those gains. These recommendations come directly from NVIDIA DevTools and are based on years of experience going through a similar performance triage process on dozens of major game titles. With trace analysis, you get hotspots sorted by perf marker and severity, the percentage of frame time taken, a severity heat map on the frame timeline, detailed explanations on multiple categories of performance issues, and suggestions on how to achieve the potential performance gain. As I mentioned earlier, it's important to validate your optimization assumptions by using Nsight Graphics with Nsight Systems. This is especially important when performance is based on resources that straddle the CPU and GPU. For example, the new resizable bar 1 feature in NVIDIA Ampere architecture GPUs allows you to fully expose video memory to the CPU, making it possible for you to improve performance of PCIe memory transfers. Resources like textures, shaders, and geometry can be requested as needed and sent concurrently without waiting for queues. To fully utilize resizable bar 1, you need to have proper visibility into how those transfers are happening behind the scenes. GPU Trace is a perfect complement to Nsight Systems when looking at improving your application's performance using resizable bar 1. Let's have a look at how you can increase shader performance. High-level shader code must first be translated or compiled into portable intermediate code, which is not GPU-specific, then to the low-level code that the GPU understands. This means that lines of shader code ends up becoming low-level instructions, which can then be efficiently scheduled to run on multiple processors, or SMs, on the GPU. Keeping all these SMs busy is what lets you take full advantage of your GPU and achieve peak performance. So what hurts your performance? Trying to do too much, or not taking full advantage of all resources available on the GPU. Specifically, let's talk about instruction stalls. GPUs are massively parallel, and so stalls can result in a massive impact to performance. For reference, the GA102 architecture features 84 SMs, and each is divided into 4 processing blocks, or partitions. Shader instructions are scheduled on an SM, or streaming multiprocessor, via a warp scheduler. Warps are groups of threads that eventually get executed. If an instruction is waiting for another instruction to finish, this dependency creates a stall, since future instructions can't be scheduled on eligible warps. Stalls limit potential performance by decreasing the number of instructions that can be simultaneously scheduled and executed on SMs and SM subpartitions. This additional warp latency is what can directly lead to poor frame rates. Nsight Graphics has a built-in shader profiler that lets you visualize where these stalls are occurring and what you should do to address them. To start, you select the Ray Tracing API event, right-click and select Profile Shaders. You are then presented with 1. A function summary that directs you towards the most expensive shader functions to consider, 2. The hotspots that you should focus on first, and 3. The event where the shader profiling originated from. The shader profiler shows you the source code for those functions with a line-by-line breakdown of stalls, and also allows you to use the dynamic shader editing feature to experiment with code changes in real time in order to see their impact on stalls. Because you can see the results of the entire compilation pipeline, from high-level shader to intermediate and down to the SAS and the NDA-only Pro version, you are able to verify that the compiler is doing what you expect. Shaders can have a huge impact on performance. Keep these things in mind when creating new shaders or optimizing existing shaders. Keep the ray payload small, reduce the number of attributes, avoid state across API calls, reduce the number of trace calls within a shader, keep trace calls out of conditional if statements, keep any hit shaders simple and try to avoid excessive amounts of alpha-tested surfaces. You can inspect ray payload, push constants, and other resources using the API inspector. We're always looking for ways to improve our tools, and in the future, we plan to introduce new features to the shader profiler to make it easier to identify and resolve those stalls. One incredibly useful feature is the ability to see scoreboard dependencies. In the screenshot above, section 1 demonstrates how we can tell you where the stall originated from. This saves a lot of time since you don't have to manually backtrace where a scoreboard stall or dependency was first created. In section 2, you'll notice 2 additional features that we're working on: live registers and register dependencies. Live registers can be important in recognizing when register pressure may be high due to excessive use of registers. Register dependencies is useful for seeing shader live state. live state can really slow down ray tracing, so it's important to keep these to a minimum. This feature will be helpful to recognize where that live state is persisted and whether optimizations are reducing them as expected. Similar to trace analysis, we wanted to find a straightforward way to visualize shader performance so that you know what you should be focusing your optimization efforts on. In general, profiling shader performance is an immense challenge that requires good intuition for what could be causing performance issues, as well as a deep knowledge of the GPU in order to know how to fix those problems. Artists are constantly changing the game world, and so being able to quickly and easily analyze a complex scene is paramount to understanding what to focus on. With the shader timing heat map, we're aiming to provide a way for you to quickly identify which areas of the scene you should be focusing on. The shader timing heat map will present you with the time spent per pixel in a shader, a heat map that provides a clear visualization of trouble hotspots and severity, and correlation between hotspots and render targets. The shader timing heat map will be available soon for both DXR and Vulkan ray tracing. Let's have a look at how the Nsight Perf SDK can help you automate your performance analysis. The Nsight Perf SDK provides you with the core technology for GPU performance counter collection. Full-featured tools like Nsight Graphics, Nsight Systems, and Microsoft's picks on Windows all use this SDK for data collection. The Nsight Perf SDK is a perfect fit for integration into 3D renderers and game editors, allowing in-place collection of GPU performance data. Imagine your artists and content creators receiving real-time feedback on the performance impact of tweaking a material or making a change to a scene. To take a measurement, simply insert an annotation into the command stream around the region of interest. Here, we are measuring a dispatch race call. There are multiple samples included in the SDK that show you how to integrate the Perf SDK library into a Vulkan, D3D12, or OpenGL application for both Windows and Linux, where applicable. The Perf SDK's built-in HTML reports can also help with low-level shader performance analysis. Determine which instruction pipelines are reaching their percent of peak or are being used inefficiently. Identify the highest warp latency reasons. Use this information to focus your optimizations on the specific instruction types implied by these counters. To see the exact lines of code that incur the highest warp latency, you can then use the Nsight Graphics Shader Profiler. The possibilities are endless for what you can do with the Nsight Perf SDK in your application. Here are some suggestions. 1. Integrate into an in-game profiler that developers and QA can use when filing bugs. 2. Generate a performance report whenever new graphics assets like shaders, geometry, or textures are checked in, allowing you to easily identify when new assets are causing performance issues. 3. Generate a performance report whenever a new build of the application is generated. Use these reports to measure performance deltas and track trends in frame rate that are correlated to performance metrics. 4. Collect performance metrics when the frame rate drops below target to better understand the reasons. If you've integrated the Nsight Perf SDK in a novel way, we'd love to hear about it. Let's talk about what you can do when you're seeing GPU crashes. With Direct3D12 and Vulkan, you're much more able to directly manage resources on the GPU. While this is great in reducing CPU overhead and improving the flexibility of custom renderers, it also makes it much more likely that bad data may be presented to the GPU. For instance, what happens if you initialize a resource that isn't pointing to properly allocated memory? You can imagine that it's not a good outcome. Now, what if this happens on a code path that is infrequently executed? Or perhaps this bug is introduced only after a certain series of steps occur. Have you ever tried debugging such a crash out in the wild when it happens sporadically to a random percentage of users? With Nsight Aftermath, you can now find out exactly where a crash occurred in your code. Specifically, you get 1. GPU mini dump files, 2. GPU state viewing in Nsight Graphics, 3. GPU subunit state, 4. Active warp PCs with the ability to map to original shader source intermediate language, 5. User markers or breadcrumbs, 6. CPU call stacks to map to source code. All of this comes with a very small footprint and an easy to integrate library. You can even decide which features of Aftermath you enable. I mentioned one possible scenario, but there are actually lots of reasons why you might get a crash on your GPU, and identifying each one of these can be difficult. Integrating this SDK into your application provides a safety net for when these issues slip through the development and QA process. It's basically a 3-step process to get Nsight Aftermath running in your application. You just enable Aftermath using the API. Set up the callbacks for what happens when a crash occurs, then insert the markers in the areas of the code that you want to instrument. When a crash occurs, you can do whatever you want with that binary blob. If you decide to save it out as a file, you can then open it up in Nsight Graphics for analysis. We highly recommend that all developers integrate Nsight Aftermath into their applications. We're continuously updating Nsight Aftermath, so if you have any questions or feature requests, be sure to reach out to us. Now let's go over some key takeaways from this session. Ray tracing is a much closer fit to how reality works, making it easier to create photorealistic applications. Verify that performance is not bottlenecked on the CPU before focusing on the GPU. Always start with the biggest performance limiter affecting your frame time, then move to the next most expensive thing. Move between Nsight Systems and Nsight Graphics to test and verify your assumptions. Modern GPUs are very fast and are great at solving the kinds of embarrassingly parallel problems that are common in computer graphics. Because of that, performance issues rarely come from serial pipeline bottlenecks anymore, but rather from performance limiters due to dependencies. Shader instruction stalls are a major performance limiter, and you should analyze your shader code to identify where dependencies are creating such stalls. GPU crashes are incredibly difficult to find. Use Nsight Aftermath to get user crash dumps that you can store in a server and later analyze. The NVIDIA Developer Tools team has a lot of great things to accomplish and is looking to grow. If you'd like to join an amazing team that does important work for a company that cares deeply about its employees, be sure to check out the careers page on the NVIDIA website. Thank you so much for watching the session. If you have any questions, be sure to ask in the Q&A or reach out using the email provided here.